So last piece of our puzzle for this unit. We've been spending a lot of time looking at kind of these activation energy diagrams. We've been looking at how we can start to kind of think about particles and collisions and how we would approach our different energies of our reactions. And so our last piece to really kind of dig into is our catalyst. And a catalyst, as we have defined before, is a substance that is not used up over the course of the reaction. It's just in there to help provide a different pathway for the reaction. So it's got its own, every catalyst works in a slightly different way. And it actually lowers the activation energy. We know that temperature increases the number of particles that get over that activation energy, but a catalyst speeds up the reaction by actually lowering the energy, making the hurdle or the hill smaller so more particles can get to that final product state. You still end up with the same products, start with the same reactants, you just end up getting there in a different way. So it lowers the activation energy, which then increases the rate constant K, and thereby increases the rate of the reaction. Your catalyst increases the rate of both the forward and reverse. Your activation energy forward and reverse is lower for both, which means they both happen faster. It yields the product faster, but doesn't make more. And that is important. It's not like all of a sudden we get magically more product forming than what we started with. We still get the same amount, we just get there faster. And that catalyst, it lowers the activation energy by providing a completely different mechanism, making a new lower pathway. And so if we think about kind of this diagram here to the right, the green was the original reaction, the uncatalyzed reaction. It was a uni-step, one bump, unimolecular uni-step reaction. The purple line here is the catalyzed reaction. And if you look, now all of a sudden we've got an intermediate here kind of in this middle valley, and then a second step, and then we can finally get to our products. But by having this intermediate step, by lowering the activation energy, we can get to the products much, much faster. And that's really the purpose of catalysts. And there's a lot of different catalysts that we can start to see. Here's kind of an example for you. So this is the catalyzed hydrolysis of an ester. So by using acid, acidified solution, we'd actually help this reaction move forward. So we're going to attach this hydrogen. Don't worry about this one. This is just an example. We end up with this resonance. And so we got these electrons that start to slide around a little bit, a lot of orgo here. But then what we end up having to do is attach this water molecule to this carbocation. Please, this is just an example, just kind of watching and learning here. As this kind of water molecule latches on, then we can kind of rearrange and break off and form then this alcohol. It turns out you can speed that up with a catalyst by having some substance that helps hold your particles in place. Sometimes that increases the rate of the reaction, or it can maximize kind of your surface area in terms of getting your molecules to collide in more efficient collisions. A lot of different ways in which our catalysts can work. So here we're actually holding it in place to help us break apart and attach more hydrogens to change our ethene into ethane. Another catalyst that we can see is how copper can help decompose acetone. We'll show that one in class. There's a lot of different examples of catalysts, catalytic converters. All of these help to speed up the reaction by lowering that activation energy. Cool. If you got questions, please feel free to mark them. I'll see you guys when you come on back.